Thank you. Right. So last time we learned how to numbering the proton signal. Okay, so proton NMR. Okay, so for carbon NMR. Okay, so yeah, we have a similar question. Okay, so yeah, if I give you one molecule. Okay, so you should quickly identify how many carbon signal. Okay, we can see for each. Okay. Right. If someone like, okay, so yeah, you can type your answer in the chat window. Okay. So again, we label this one as A. Okay, so this one as B. Okay. And just one thing, keep in mind. Okay, so the carbon NMR signal, it's not necessarily same as the proton NMR signal. Okay, so yeah, for the first one we already learned we practiced it before. Okay, so yeah, the first one we can see totally 4 proton signal. Okay, so yeah, 4 proton. Okay, so now the question for you guys kind of how many carbon signal we should see for it. Okay. Right. Anyone know the answer? Okay, you can take a try. We type in the chat window. Okay, how many carbon signal we should see for A? How many the carbon signal we should see for B? 5. Yeah, that's perfect. Okay, that's the right answer. Good. All right, so yeah, carbon NMR. Okay, so similar to the proton NMR, you try to find symmetry or kind of rotation axis. Okay, symmetry plane. Okay, so yeah, if 2 carbon relate by kind of rotation axis symmetry plane, you have kind of same chemical shape. Okay, all right, so here these 2 methyl. Okay, so carbon same 1, and then 2, 2, right, and then 3, 3. Okay. And then these 4 carbon will be same, okay, because they are related by kind of a simple plan rotation axis. Okay. All right. In the end, okay, don't forget these 2 carbon. Okay. So these 2 carbon, yeah, have no hydrogen attached to it. Okay, but yeah, you should see it on the carbon NMR. Okay. So yeah, these 2 are symmetrical to each other. Okay. So that's 5. Okay. So totally, you should see 5 carbon signal for this molecule. Right, and then for the second one, okay, so yeah, the casing is here, okay, so yeah, the chiral center, okay, similar to the proton NMR, okay, so if there's a chiral center, okay, OCH2, okay, the 2 hydrogen on the same carbon will show different chemical shape, okay, because they become the DR topic, okay, and similar thing for here, okay, so these 2 methyl, okay, so yeah, because of this chiral center, okay, these 2 methyl will show different chemical shape, okay, because they become kind of DR topic. Okay, so if you replace one with a D or maybe some other the atoms, okay, so each time, okay, and then yeah, you generate kind of a pair of DR stereomers, okay, so these 2 will different, okay, and because this the chiral center, okay, so we will totally break up all the symmetric, okay, and then all the carbon will show different chemical shapes, okay, so 1, 2, 3, 4, 5. And then these 2 will be different, okay, 6, 7, okay. So for B, you should see kind of totally 7 carbons, okay, 7 carbon signal, okay. Yeah, make sure you know how to do this kind of question, okay. So we'll have a very similar one in the coming maybe quiz 6 or exam 3, okay. Exam, yeah, that's right. Yeah, okay. So let's do this, okay. So because there's chiral center, okay. So yeah, if you replace the 1 carbon, okay. So yeah, with some kind of maybe A, okay. So yeah, just the letter A, okay. And then we replace probably with this one with A, okay. And there's the hydrogen here, okay. And then we generate a pair of DR stereomer, okay, DR stereomer, okay. So 1 stere center same, 1 stere center opposite, okay. So, and then this 2 methyl group will be DR topic. They will have a different chemical environment, okay. So and also they will have kind of different chemical shape, okay. So that's the please keep in mind, okay. Very similar to the CH2, okay. So if there are kind of for example these two hydrogen, okay, have different chemical shapes because they're their centers, okay, so yeah. All right, good, okay. So next kind of yeah, we'll learn yeah, a very special the carbon NMR called the DAPT NMR, okay. So yeah, this one a little bit hard, okay. Please a little bit focus on here, okay. So DAPT NMR actually kind of not only one single spectrum, okay. Actually kind of yeah, three spectrum kind of yeah, kind of overlay together, okay. You generate kind of DAPT NMR, okay. And then yeah, normally the first one is kind of yeah, we call it the DAPT 90, okay. DAPT 90, okay. DPT, okay. And then second one we call it the yeah, DAPT 135, okay. And the last one just the yeah, no more carbon NMR, okay. And quite often yeah, people also call this the decoupled kind of broadband decoupling kind of carbon NMR. Just the carbon NMR we already learned, okay. So that's three carbon NMR relate to each other, okay. So then yeah, if you combine these three carbon NMR, okay, and then you can yeah, know how many hydrogen attached to individual carbon, okay. So yeah, we learned kind of yeah, totally four kind of carbon, okay. First is quaternary carbon, no hydrogen attached, okay. And then second is the yeah, tertiary carbon, okay, so only one hydrogen attached to it, okay. And then the third one kind of we call the secondary carbon, okay, two hydrogen, and then in the end, okay, primary carbon, okay, so three hydrogen attached to it, okay. All right, so what kind of signal you should see kind of on the DAPT, okay. So if it's the yeah, CH2, only CH1 hydrogen, okay, on the yeah, carbon, okay, so yeah, you should see kind of the positive signal in the yeah, DAPT 90, okay. Positive signal. I use kind of plus indicator positive signal. And for quaternary, secondary, primary cannot show signal kind of on the DAPT 90, okay. Only yeah, this quaternary, tertiary kind of carbon, okay, so one hydrogen attached, okay. All right, and then for the DAPT 135, okay, so we are the yeah, get more complicated, okay. So yeah, you can see positive signal for both yeah, CH and also C3, okay. Quaternary carbon, tertiary carbon, and also the yeah, primary carbon, okay. So these two will show kind of yeah, positive signal, okay. And then for CH2, okay, secondary carbon, okay, so you will see kind of negative signal, okay. Okay. And eventually, okay, so we are for the normal carbon NMR, okay, no carbon, advanced kind of carbon will show kind of a positive signal, okay. So yeah, even for the quaternary carbon, tertiary, secondary, and primary, okay. So all will show yeah, the yeah, positive signal, okay. So yeah, probably I still real. Right. So in this case, combine these three carbon NMR, okay, so you should able to tell kind of how many hydrogen on each individual kind of the carbon, okay. Very useful, okay. Right, how do you read the DAPT, okay, so that's three. So first, yeah, you need to read the DAPT 90, okay, DAPT 90, okay, so yeah, that tell you kind of the yeah, which carbon has only one hydrogen on it, okay, so yes, DAPT 90. Okay. All right, and then second kind of read the DAPT 135, okay. Yeah, if you have any question, okay, just yeah, please type in the chat window, okay. All right, so DAPT 135, either one kind of the CH2, okay. So if you see any negative yeah, signal in the DAPT 135, okay, that should be the CH2, okay. And then yeah, if you see the positive signal, okay, so yeah, if this positive signal also showed in DAPT 90, okay, that should be CH, okay. So if this positive signal, okay, doesn't show in the DAPT 90, okay, so that should be CH3, okay. And eventually, okay, so yeah, yeah, look at kind of broadband, okay. So if one signal, okay, doesn't show in either DAPT 90 or 135, okay, so that means kind of quaternary carbon. Quaternary carbon cannot show in the DAPT 90 and 135, okay. By combine all this information, you should able to know how many the hydrogen on individual carbons, okay. I kind of help you resolve the structure, okay. Okay, and then here's one example, okay. So that's the DAPT NMR, okay. So this time, okay, so we put the normal carbon NMR on the top, and then DAPT 90, and then DAPT 135, okay. Right. So yeah, there should be the 5 different carbon, okay, so yeah, on the in this molecule, okay, so yeah, 5 signals, okay, so there's the red one, blue one, kind of quite close to each other, okay. Right, and then when you look at kind of depth 90 first, okay, you find kind of this blue signal, okay, showed up in the depth 90 as kind of positive, okay. So definitely means here this blue signal, this one, okay, is the CH, okay, because only the CH showing the CH carbon, okay, showing the depth 90, okay. Right, and then following we look at the depth here, the 135, okay. So yeah, look at the negative peak first, okay. So that's this 2 red one, okay. So that should be a CH2, okay. CH still here, okay. Right, and the CH2, okay. So and then in that case, so yeah, this green one, okay, okay, positive, but didn't show it yet, in the depth 90, okay. So that will be CH3, okay. Eventually, okay, so you look at broadband one, compare it with the depth 90, depth 135, okay. So yeah, you find one actual peak that showing depth 90, also depth 135, okay. So that's means this is quaternary carbon, okay. So yeah, that's help you identify kind of which carbon is which, okay, how many hydrogen are, okay. So this is the depth NMR for SO2 propanoate, okay. And so yeah, carbon one, okay, so that's the ester carbon, okay. So this one has no the hydrogen attached with quaternary carbon, so that's why only showed in the broadband carbon NMR, okay. And then carbon 2, okay, so yeah, that's CH, only hydrogen attached with, okay, so that's shows in depth 90, okay. And then carbon 3 and also carbon 4, okay, CH2, okay, showed as the negative signal, okay. Okay, so in the captive one, depth 135, okay, so that's the these two has two hydrogen attached with it. Eventually CH3, okay, so only show negative positive in the 135, okay, so that's the CH3, okay, so that's very useful, okay. All right, okay. So now we do a little bit of practice, okay. And here kind of just use the depth NMR help you figure out the structure of a molecule, okay. Okay, so here we have C5H10Br2, okay. So once you have one the formula, okay, so that's the formula, okay. And then this is depth 90, 135, okay, and then broadband, okay. So once you have the formula at hand, first thing you need to do is kind of calculate DU number, okay. Can anyone tell me what's the DU number for this molecule? Okay, C5H10Br2. Okay. Yeah, can anyone type the DU number in the chat window? First thing you need to do kind of that's right, the DU equals 0, okay. So this morning kind of the couple students kind of give wrong answer, okay. So current stage, okay, you have to know how to do the DU number calculations, okay. Otherwise, you cannot survive in quiz 6 and also exam 3, okay. All right, okay. So next kind of maybe give you guys half a minute, take a try, okay. So try to figure out its structure, okay. So if you like, you can also turn on the annotation, okay. Try to draw structure for it, okay. Right. So here's some kind of hint, okay. So first the DO equals 0, okay. So that means here there's no ring and also no double bond in the molecule, okay. So just kind of the carbon chain, okay. Right. And the second case, so depth 90, there's no signal, okay. Depth 90, no signal, okay. So that means there's no CH, okay. All right, and then depth 135 only showed the negative signal, okay. So there's 3 CH2, okay, 3 CH2, okay. And interesting is the broadband, okay. So normal carbon NMR, okay. So also only show these 3 signals, okay. So the 3 small peak at the 77 is the chromophore, okay. So that's the node from sample, okay. So that means in this molecule, okay, only 3 kinds of CH2, okay. Right. But we know that kind of should be 5 carbons, okay. So that means there are some kind of symmetrical king in the molecule, okay, in this molecule, okay, plus 2Br, okay. 3 CH2, okay, but totally, 2Br. But totally is kind of 5 carbons, okay, but here we only see 3 kind of CH2, okay. So anyone has this idea, okay, what's kind of the structure can give this kind of the carbon number, okay? Only CH2. Yeah. All right. So this is the little bit hard one, okay. So keep in mind, okay. So for the saturated kind of we call it maybe the carbohydrate, okay. So you should have kind of CH3, okay, as terminal group, okay. Terminal, okay. So like the carbon chain, okay. CH3, okay. But here there's no CH3, okay. So only CH2, okay. So that means this molecule, okay. So the one of the hydrogen in the CH2, okay, CH3, okay, replaced by Br, okay. Maybe we'll do this way. So that's still become a terminal one, okay. One, okay. Okay, and because there are a lot of symmetrical in the molecule, okay. So that means you should have 2 of this one, okay. 2 of this one, okay. Right, and then 14 case, so just the bunch of CH2, okay. And then another CH2 with Br. Okay. Actually, this is the answer for this question, okay? Right, okay. Because there's the simple plane rotation axis cuts this molecule, okay? And these 2 CH2 will show 1 signal, okay? So that's 1. These 2 will show another CH2 signal, okay? 2, and then 3, okay? So that's why for the whole molecule, okay, so there are totally 5 carbons, but here only you see kind of 3 CH2, okay. Yeah. Right. So that's one way to show the depth limit, okay. Another way to show it is we use this kind of spectrum, okay. So the still carbon limit, okay, but in the carbon case, so in the molecule case, so the signal, okay. So we labeled how many hydrogen attached to individual carbons, okay. So for example, here the first one just C, okay, that means kind of quaternary carbon, no hydrogen attached to it, okay. And then CH2, okay, so C3, CH2, CH, C3, okay. So that's this kind of carbon number is another way to show the kind of depth number. This directly tell kind of how many carbons, okay, and how many hydrogen on individual carbons, okay. All right, and so the formula is C6H12O, okay. Ask kind of what structure for this molecule, okay. Again, okay, can anyone tell me what's the degree of saturation for this molecule? Okay, someone already gonna try that, good, okay. Yeah, take a try, okay. All right, that's good, okay. Carbonyl group, okay, that's right, okay. All right, so someone know it's kind of carbonyl group, okay, that's right, okay. All right, okay. All right, okay. Keep in mind, okay, totally 6 carbons, okay. So now I show kind of the 2 branch, okay. So but only 4 carbon totally, okay. All right, take a try, okay. But the good thing for this student kind of he or she know it's the ketone, okay. That's pretty important, okay. All right, can anyone finish the drawing of this unknown structure? Okay. Yeah. A pretty good one, okay. One, okay. No, don't worry, okay. You guys can work together, okay. All kind of Okay, someone else want to try. Okay, that's good. Okay, take a try. Okay, so you can turn the annotation. 1, 2, 3, 4, 5. 5 carbon, okay. But we have totally 6 carbon here, okay. Where's another carbon come from? or is another carbon we touch with. 1, 2, 3, 4, 5, 6. Okay, that's 6 carbon. Okay, so that's close. Okay, but here the not exactly right answer. Okay, not exactly right answer. Okay. All right. Okay. So this is a relative hard one. Okay, but yeah, if you give me the answer like you guys just showed, okay, so probably at least on half of the points. Okay. Okay, so for this kind of question, okay, so first kind of you need to generate kind of all the fragment, okay. So yeah, we see already there's kind of quaternary carbon, okay, at around like the 200, okay. So yeah, and then that means carbonyl group, okay. So that's already something you kind of know it, okay. So pretty good, okay. So once you know it's carbonyl group, okay. So yeah, first you need to kind of how many kind of oxygen or maybe other heat atom, okay, in the formula, okay. So if 2 oxygen, probably ester or kind of carbonic acid, okay. And if only 1 oxygen, like this case, okay, so that's has to be the ketone aldehyde, okay. Okay, so all other carbonyl compound, okay, have more than 1 oxygen or maybe other heat atom, okay. So yeah, it is ketone aldehyde, okay. So look at kind of here, that's quaternary carbon. Quaternary carbon means kind of no hydrogen attached to it. Okay? So if aldehyde is kind of 1 hydrogen attached, okay. So that means ketone, okay, that's good, okay. That's first fragment, okay. And then second case, so yeah, we have the CH2, okay, so yeah, CH3, CH, C3, okay. All right, okay. So now you need to add all the carbon and also hydrogen together, okay. So you find we get kind of C5H9O, okay. So but the former kind of C6H12O, okay. So that means you miss CH3, okay. So that means one of these C3, okay, actually is showed kind of same signal, okay. So or in other words, okay, 2 C3, okay, same kind of chemical shape, okay. Right. So that's you have all these fragments, okay. And then following kind of important kind of how do we combine them, okay. So one case thing kind of if 2 C3, okay, showed in the same chemical shape, okay, so that means this 2 C3 has to be attached on the same carbon, okay. All right, so that you can merge these 2 fragments, actually these 3 fragments together, okay. So somehow generate kind of isopropyl group, okay. So that's this 2C3, okay, will be symmetrical, okay, so same chemical shape, okay. All right. Okay, so now we have kind of this fragment, and ketone, okay. All right, so ketone, okay, so just keep in mind, okay, so carbon, okay, next to ketone, okay, have higher chemical shape, okay, so that's we need kind of put this 3 fragment ketone on kind of 2 sides of ketone, okay, 2 sides of carbonyl, okay. All right, and then we look at here, okay, so we have CH2 and also CH3, okay, relative high chemical shape, okay, so higher than others, okay. So that means one end of this ketone is C3, another end CH2, okay. So that's give you higher chemical shape, okay. Cannot be this CH, okay, because the CH kind of lower than CH2, CH3, okay. All right, and then so that's how do you kind of merge together, okay. And eventually, okay, so this end, okay, you put CH and then 2 mass one. Okay, so that's the final structure, okay. Yeah, carbonyl, okay. And then you add kind of C3, C2, okay, because this we call the carbonyl hydrogen, okay. So that's the higher chemical shape, okay, and then eventually isopropyl group add on. Okay, so that's how to use all these questions. Okay. All right, okay, so we'll do more practice later, okay, so don't worry, okay. Here just summary of some important functional group, okay, it's NMR, okay, so both proton NMR and those carbon NMR, okay. Although we have the chart, okay, so here, okay, so both the carbon NMR chart and also the proton NMR chart, okay, so you can bring it with you for your future exam quiz, okay. But my suggestion kind of for some important kind of shift, chemical shift, okay, keep a little bit in idea, okay. So that's will save you a lot of time in the future exam quiz, okay. All right. Right, we do it one by one, okay. First, from alkene, okay, alkene just pretty low, okay, for hydrogen, okay. So from the proton number, okay. So 0.8 to 1.7, and okay, someone ask questions. Okay. So to make sure that the 2ACH3 have same chemical shape, okay, same kind of the carbon and image signal, okay. So they have to on the same carbon, okay. So in this case, you have symmetry plane rotation axis related to the CH3, okay. Okay. Right. And also important kind of there's no chiral center in this molecule, no chiral center in the molecule. So that's 2CH3 will have same chemical shape, okay. So so if there's chiral center, okay, so the 2CH3 will have different kind of chemical shape, okay, isopropyl, okay. So so no steric centers, okay. For example, isopropyl group 2C3 will have same chemical shape, okay. All right, no problem. Okay, so now we do it one by one, okay. So alkene, okay. So alkene, okay. So although the OCH, C3, CH2, okay, similar chemical shapes, okay, but I want you guys a little bit keep in mind, okay. So C3, okay, about the 0.9, okay, so and then followed by CH2, okay, so 1.3, okay, and then followed by CH, okay, 1.5, okay, so more carbon, okay, so then you have kind of little bit higher chemical shape, okay, and the carbon number, okay, so 10 to 60, okay, so that's quite normal, okay. Right, and then here, okay, so the first proton number, I want you guys kind of little bit keep idea, kind of alkene kind of hydrogen, okay. So that's the hydrogen directly attached kind of city bond, okay. So this one, okay, so normally I don't try to remember the range, okay, 4.6 to 5.7, okay. So that's too many numbers, okay. So normally I just remember kind of around 5, okay, around 5, okay. So so normally no other kind of proton will show signal around 5, okay. So if you see proton around 5, okay, more likely it should be the alkene protons, okay. And those for alkene carbon, okay, so normally the chemical shapes they are from 100 to the 160, okay, 160, 160, okay. All right, and then next a little bit keeping mind kind of the benzene proton, okay. So benzene proton, okay, so just remember around 7, okay. So don't you remember 6.5 to 5.8, okay. 8.5, okay, so just remember around 7, okay, so that's also very unique, okay, so normally no other proton show in this area, okay. And so benzene carbon, okay, similar to the alkene carbon, okay, so around like 100 to 160, okay. Right. And for alcohol, okay, alcohol OH group, okay, so chemical shapes can be anywhere, okay, because the sensitive kind of temperature, pH, okay, concentration, whatever, okay. And the last predictable, okay. But the alcohol peak quite unique, okay. So normally quite broad and also singlet, okay. So if you see some kind of broad singlet peak, okay, so normally that means that's alcohol proton, okay. So for example, showed here, okay, so that's broad singlet, okay, so that's alcohol, okay. No other the proton should be kind of much sharper, okay. And so one thing I want you guys a little bit keep in mind, okay. So for the CH, okay, so the hydrogen, okay, so this carbon attached kind of oxygen, okay. So that's how do we call that kind of the carbon adjacent to kind of OH, okay, so it has kind of hydrogen, okay. So this hydrogen, okay, so about like the pretty high, okay, so 3.4 to 4.0, okay, so pretty much you can just write down kind of 4, okay, about 4, okay. So normally speaking, kind of there's no other heat atom, okay, so just kind of the pretty low, okay, so but oxygen strong electron withdrawing effect, okay, deshielding, okay, around 4, okay, so that's the little bit keep in mind, okay. Right, amine, okay, so amine NH, similar to alcohol, okay, so the can be anywhere, okay, so relative broad peak, okay, so So region can be 0.5 to 5.0. Okay, so that's hard to say. Okay, so yeah. Okay, and aldehyde ketone. Okay, so aldehyde. Okay, so that's another thing kind of little bit keep in mind. Okay, so aldehyde proton. Okay, so pretty high helical shape. Okay, about like 10. Okay, just remember 10. Okay. And so another kind of the important proton. Okay, so I want you to keep in mind kind of they call the hydrogen on alpha carbon 2 aldehyde ketone. Okay, so 2.1 to 2.6. Okay, so what's that mean? Okay, so you have aldehyde ketone, carbonyl. Okay, and then this hydrogen, this one. Okay, so that's we call kind of actually carbonyl. Hydrogen, carbonyl hydrogen. Okay. Carbonyl hydrogen. Okay. So this one about you just remember kind of 2.3, 2.5. Okay, right. So don't exactly kind of remember the whole range. Okay, so remember the center value. Okay, and so that's different from kind of other hydrogens. Okay, so if we see no helium atom. Okay, also kind of no carbonyl. Okay, so should be around like 1. Okay, so this one kind of relatively high. Okay. And for the carbonyl kind of compound, the carbon case signal kind of pretty high, okay, around 200. Okay, so that's where we already learned that. Okay, so it's better ketone and aldehyde, okay, pretty high. Okay, and carboxylic acid. Okay, so carboxylic acid. Okay, so here the pretty unique ones here, the COH. Okay, so the SH. Okay, so the SH here the pretty high. Okay, about 12. Okay, so that's here the probably the highest kind of the chemical shaped case, so we learned so far. Okay, so this HK OH. All right, although it's OH case, that's different from the alcohol OH. Alcohol OH never can reach the above 10. Okay, and so for the carbonyl capacity case, so that's the little bit lower than aldehyde ketone case, so about the 170, 180 something. Okay. All right, okay, so now comes kind of important part, okay, ester. Okay, so this morning kind of your student got confused, okay, about ester. Okay, so ester, when we learn naming, already know that kind of has 2 parts. Okay, the one part kind of the 2 alkyl group. Okay, so one alkyl group. Okay, R1 attached kind of the carbonyl. Okay, another alkyl group. Okay, attached kind of oxygen. Okay. All right, okay, so the key things here. Okay, so normally note hard kind of figure out kind of R1, R2, okay, and also ester. Okay, important kind of you need to figure out which one attached kind of carbonyl, which one attached to the alcohol. Okay, OH, okay, oxygen. Okay, because they are 2 kind of we call the isomers. Okay, right. So I just draw both. Okay, so first one R1 attached kind of carbonyl. Okay. R2 attached to oxygen, and then second one, okay, R1 attached to oxygen, and then R2 attached to the carbonyl. Okay, right. How do we figure out? Okay, so the key thing here. Okay, so remember. Okay, so if we see the carbon directly attached to oxygen, its hydrogen will be around like 4. Okay, so if the carbon attached kind of carbonyl, okay, its chemical shape about kind of 2.3. Okay. So based on the chemical shape and the split part, okay, you should able to tell which alkyl group are bound kind of the carbonyl, which one bound to the oxygen. Okay, here's one example. Okay, in acyl acetate, okay, and also the methyl propionate. Okay, so both actually kind of the isomer to each other. Okay, so there's there are one acyl group. Okay, one acyl group. Okay, one methyl group. Okay, and acyl acetate. Okay, so methyl group attached carbonyl, ethyl group attached oxygen. Okay, so methyl propionate. Okay, so ethyl group attached kind of carbonyl. Okay, and then methyl bound to kind of oxygen. Okay, all right. How do we distinguish this? Okay, so they have very unique here the split pattern and also chemical shape. Okay, so for the this methyl group, okay, it should be singlet, okay, and then relatively low chemical shape, okay, because bound to kind of the carbonyl. Okay. And then for this ethyl kind of CH2, okay, so that should be quartet. Okay, we use N+1 rule. Okay, so 3 neighboring hydrogen. Okay, so 4 peaks. Okay, but this quartet should have a higher chemical shape because of the single oxygen. Okay, right. And so in this case, for the acyl acetate, you should see kind of the quartet has higher chemical shape than singlet. Okay. And under the methyl kind of the propanoate, okay, so the kind of they have kind of reverse kind of position, okay. So the singlet, okay, so attach kind of oxygen, and then higher composite, okay, and then quartet attach kind of the carbonyl, okay, lower composite, okay. Here show their kind of real the spectrum, okay, proton number, okay. So first one kind of SOS, okay, so because this quartet, okay, so CH2 attach kind of oxygen of higher composite, okay, and this singlet kind of this methyl, okay, attach kind of carbonyl, okay. And then for the methyl propanoate, okay, so the singlet and also the quartet position kind of switch, okay, because the singlet, okay, so that's this methyl attached with this oxygen, okay, and then this the quartet kind of the ethyl, okay, so attached kind of carbonyl, okay, so this singlet should have kind of higher composite than this quartet, okay. So based on their kind of three part and relative position, okay, so you should able to tell kind of which part attached to carbonyl, which part attached to kind of oxygen, okay. Very kind of unique and also important technique, okay. All right, okay, so now we do a practice, okay. Right, so I can tell you this molecule, okay, C5H10O2 is an ester, okay, okay. Right, and then next kind of you guys need the take try, okay, figure out the structure, okay, and then figure out which part attached kind of the oxygen, which part bonded to carbonyl group, okay. Right, take a try, okay, give you guys 1 minute. All right, so right, if you like, you can turn annotation, draw the structure, okay. Right, so for this one, we already know there's a carbonyl group, okay, in the ester, okay. Right, that's true, okay, ester, okay. And you need to figure out the first, okay, so you need to figure out kind of what's R1, R2, okay. All right, someone draw the structure, but not exactly right, okay. Think about it, okay, okay. So if you draw me this one, probably I'll give you maybe 1/3 of points, okay, so Right, you have to look at the proton number, okay, so we have 1 proton here, 3 proton here, and then 6 proton here, okay. All right, okay. So I guess this one probably I will do together with you guys, okay, again, okay. All right, so we already have we'll do it stepwise, okay, no rush, okay. So okay, so we already have 1 fragment, okay. So and then all other fragments from this proton number, okay. So 1 hydrogen, okay, 1 hydrogen means it's CH, okay. And then you can also put its multiplicity on it, okay. So there's many peaks, okay. So if you don't know count it, okay, you just kind of put M, okay. Right, and then there's CH3, okay, 3 protons, okay. So next, okay, CH3. Okay, CH3, okay, so this one's singlet, okay, pretty interesting case. That's means kind of no neighbor hydrogen, okay. All right, and then falling case, so we have kind of the 6 hydrogen, okay. 6 hydrogen means kind of 2 CH3, okay. 2 CH3, okay, and then this 2 CH3 kind of both doublet, okay, same composition, okay. Doublet. Right. And then afterwards, okay, so don't forget, okay, add all the hydrogen, carbon together, okay, and then oxygen, okay, to see whether it kind of fit with the C5H10O2, okay, so so 1, 2, 3, 4, 5, okay, 5 carbon, no problem, okay, so and hydrogen, okay, 1, 4, okay, and then plus the 6 here, okay, so 10 hydrogen and 2 oxygen, okay, so all the atoms are countable, okay. Yes, okay, you need to pay attention to the number of peaks, okay, okay. All right, okay, so now we have all of the we can see kind of the 5 actually kind of 5 fragment, okay. Okay, so now how do we kind of combine them together, okay? So that's kind of important thing called the split pattern, okay? Okay, so you see this is a doublet, okay? So that means here this CH2, okay, have CH as its neighboring hydrogen, okay? CH2 as his because the doublet, okay, means n plus one rule, okay? So that's only one hydrogen as neighboring hydrogen, okay? And actually kind of we learn this here the split pattern, okay? So singlet septet, okay? Actually kind of this one is septet, okay? Singlet septet, and then 6 here the proton doublet, okay? Typical isopropyl, okay? Okay? So that's here we can merge this here 3 fragment, okay, like this. Right, so that's here D and D, and then this is the septet, okay? All right, okay. So now, we kind of the shrink it to the 3 fragment, okay, methyl, and then here, okay. All right. So now my question for you guys, okay. So can anyone tell me kind of the okay, so we do here, R1, R2, okay. So which is R1, which is R2, okay. So which one bound to carbonyl, which one bound to oxygen, okay? Right, and one take a try, okay? So we just learned it, okay? How do we determine kind of the acid structure, okay? So it's which one bound to kind of carbonyl, which one bound to oxygen. Yeah, that's right, okay? Isopropyl bound to oxygen, okay? Pretty good, okay? So keep in mind, okay? So the functional group, okay, bound to oxygen has a higher chemical shape, okay, and then another one, okay, so we are bound to carbonyl, okay, lower chemical shape, okay, and then look at kind of the NMR spectrum, okay, definitely kind of isopropyl, okay, so isopropyl kind of the CH has much higher chemical shape than kind of CH3, okay, so that's how do you identify, okay, so pretty good, okay. Right. So once you have kind of 3 fragment, okay, so isopropyl, methyl, and also ester, okay, so 2 possible ester structures, okay, so and then the oxygen, the isopropyl bound kind of oxygen because this one has higher chemical shape, okay, so that's where, so it's kind of oxygen one has higher chemical shape, okay, so all right, good, okay. Right, here's kind of just the tell you what kind of information you can get from NMR, a little bit summary, okay, for this chapter, okay. So both carbon NMR, proton NMR can provide a number of signals, okay, someone said kind of potential kind of peak signal, okay. So that's the different kind of the carbon signals, okay, different kind of the proton signals, okay. And then both carbon NMR, proton NMR kind of chemical shape can tell what kind of functional group, okay, what kind of chemical environment, okay. So like aldehyde, okay, or ketone, whatever, okay, so and then only proton NMR can provide the integration, okay, that's tell kind of how many hydrogen for each type, okay, and coupling kind of very useful, you already know that kind of can help connect all of the fragments together, okay, and eventually give kind of the final structure, okay. All right. Okay, so there's a very difficult type question, okay, for the chapter 14 is the combined spectral problems, okay. I also call kind of comprehensive kind of spectrum problem, okay. So this type case, so normally give you the formula and then also IR and also the proton NMR, carbon NMR as kind of fake out structure, okay. The first thing you need to do kind of calculate DU number, okay. So if you cannot do DU number calculation, that's very tough for you to solve the structure, okay. And then second kind of you try to extract and functional group information from IR, okay. So is that a carbonyl or maybe some kind of the amide or some kind of other, okay. So that's also pretty useful, okay. And then eventually, okay, so you need to analyze the proton NMR, okay. Try to generate kind of all the small fragment, okay. And make sure, okay, don't forget here, because that's quite often, okay. You add all the carbon, hydrogen, oxygen, whatever, okay, together, okay, and then check with original kind of the formula, okay. So make sure it's matched, okay. So if there kind of missing atom, okay, so maybe there kind of the symmetrical in the molecule, symmetrical, okay. So right, and also you need then you use the split pattern, okay, try to merge all the fragments together, okay, and then eventually generate kind of maybe 1 or 2 reasonable structure, okay, and then you have to double check with the structure with the old spectrum. Okay, so if it kind of the fit all the data, okay, that will be kind of right structure. Okay, yeah. So that's not easy question, but we will learn it kind of little by little. Okay, so we will do a lot of practice on it. Okay, right, here's one. Okay, and so this is the C5H9BR02. Okay, so this is the structure. Okay, this formula already provided you. Okay, and also I already provided you kind of DO number. Okay, so it will some time. Okay, and then provide you IR and those the proton number. Okay, and ask kind of what structure for this molecule. Okay, so once you have the DO number. Okay, so then you need to cut kind of carbonyl. Okay. Can anyone tell me kind of what kind of functional group in this molecule? Okay, so just by looking at the IR, okay, right, the hint is here. Okay, what kind of functional group in this molecule? Yeah, that's right. Okay, carbonyl. Okay, CO double bond. Okay, so remember IR. First thing you need to look at kind of is any peak around 1700 carbonyl. Okay, all right. So that's the once you have know that kind of carbonyl group. Okay, so then you look at kind of formula. Okay. So look at kind of the oxygen. How many oxygen here? Is any kind of nitrogen or kind of chloride here? Okay, so no nitrogen, no chloride. Okay? That means cannot be amide, cannot be S chloride. Okay, and 2 oxygen. Okay, so there are only 2 kinds of functional group. Okay, has the 2 oxygen. One's carboxylic acid, one's ester. Okay, can anyone tell me it's ester or carboxylic acid? Right, 2 oxygen, ester or acid. Okay, in this molecule. That's right. Okay, ester. Okay, ester. Okay, good. Okay, so if it's carboxylic, okay, should be very broad peak. Okay, so from 2400 to 3400. Okay, so that's the ester. Ester, we should have kind of CO stretching. Okay, single bond stretching around 1200. Okay, so that's true. Okay, so that's 1200. Okay, and then last here we have first fragment. Okay, yeah, first fragment. Okay, that's ester again. All right. Okay. So next kind of because of your time limitation, I just show you how to resolve this question. Okay, right. Next kind of you need to generate kind of all the small fragment. Okay, so we do it from left to right. Okay, so from NMR. Okay, so 2 hydrogen. Okay, so that should be CH2. Okay, so don't forget. Okay, you can also write down kind of split part. Okay, so the first one. Okay, looks like quartet. Okay, 4 peaks. Okay. And then second one, okay, so another CH2, okay, so looks like a triplet, okay, 3 peaks. Okay. And then third one, also the CH2, okay, also 3 peaks, triplet, okay. And last one, kind of the 3 hydrogen, okay, CH3, okay, and then that should be also triplet, okay. Right. Okay, and then following case, so we have all the carbon, hydrogen, okay, and then oxygen. We need to add them together, okay, and look at kind of compare with the former, okay. So 5 carbons, okay, and then hydrogen, okay. So that's 4, and then 5 was 9, okay, 9 carbon, 5 hydrogen, okay, and then 2 oxygen, and then 1 bromine, okay. Okay, so that's here we have all the fragment, okay. So following thing, okay, how do we combine the fragment together? Okay, that's hard thinking. How to kind of merge them together, okay. Okay, so look at kind of split pattern. We need to use the N+1 rule. Okay, so that's here the important thing. You guys can write it down. Okay, so always start from kind of CH3. Okay, always start from CH3. Okay, so because CH3 has only 1 attachment. Okay, so definitely you know it's kind of how many neighboring hydrogen. Okay, so for example, this CH3 kind of triplet. Okay, so that means kind of the CH2 next to it. Okay, so that's give kind of triplet. Okay, CH2, 2 hydrogen, 2 + 1, 3 triplet. Okay, always from this guy CH3. Okay, never start from kind of CH2. Okay, because CH2 has 2 attachment. Okay, you don't know kind of what kind of attachment. For example, here the quaternary is the first one. Okay, quaternary. Okay, so that's 3 hydrogens. Okay, could be 1 methyl and a quarter carbon, or could be kind of the 1 methyl, okay, 1 CH and 1 CH2, okay, so all can give kind of quaternary kind of, okay, from this one, okay. All right, so that means here this CH3 will bond with the one of this CH2, okay, one of the CH2. Which one is bonded, okay? Will be this guy, okay. Why is this one, okay? Because this one is quaternary, okay. Quaternary means it has the 3 neighboring hydrogen, okay, 3 + 1 give kind of 4 peaks quaternary, okay. So if it's here the bound to these two CH2, okay, so this won't be kind of a triplet, okay, right? So that's here automatically bond these two together, okay. That's here to give you the CH2, CH3, okay, merge one, okay. And then following case, so these two CH2, okay, both are kind of triplet. That means kind of these two should be next to each other, okay. CH2, CH2. All right. So that's how do we merge them together, okay. So that's here the quartet, okay, triplet, okay, and then triplet, triplet, okay. So that's you have to make sure we double check, okay. And eventually, okay, so we have one bromide here, okay. So one bromide, okay, so definitely kind of put on here, okay, because if you don't want to put here, okay, so if you attach to this the CH2 attach here, okay, get more stability for this one, and also the other kind of terminal one, okay, so that's no way, okay, so okay. All right, so now we have kind of two fragment, okay, okay, and then ester, okay, so similar question, okay, assuming this is R1, this is R2, okay, can anyone tell me, okay, so which one bound to an oxygen, okay, R1 or R2? Last question for today, okay. Which one bound to the oxygen, R1 or R2? Yeah, that's right, okay. R2, okay, R2, pretty good, okay. You guys know how to solve ester questions, okay. Right, so R2, you need to look at the which one has higher chemical shape, okay. So that's here the quartet, okay. So that CH2 with quartet has higher chemical shape, okay. That means here this guy bound to oxygen, okay. So that's here the higher chemical shape, okay. All right, so now we can do it, okay. C2, C3, and then another CH2, bromide, okay, bound to kind of the carbonyl, okay. Yeah. All right. Okay, that's it for today. Okay, so we'll do more practice here on Wednesday, okay, before we start the new chapter. Okay, and also we'll also do some practice in the discussion on Thursday. Okay, and then we can have the quiz 5. Okay, so on Wednesday we'll vote it. Which day do you guys want to take the quiz 5? Quiz 6. Sorry, should be quiz 6. Okay. Right, so that's done the class today. Okay, thank you. Have a good day. Okay.